Welcome. So far, we have studied all the theories of the heat transfer, mass transfer, and energy transfer for the balance. And many times you see that we are landing up with many kind of mathematical problems, and in those problems, we find that we are sometimes representing all those model equations. For example, the Navier-Stokes equation in terms of some partial differential equations, and sometimes we are reducing them to ordinary differential equation. In any case, what we find that we are sometimes having some scalar quantities like the temperature, the concentration, etc. And sometimes we are having some vector quantities like the velocity, momentum, force, etc. Now, whatever we are doing, ultimately we are having some kind of mathematical equations to be solved for. And whenever you are going for solving, in the books, in the literature, you will find that many notations are used to represent all these equations. So, in conclusion of this particular subject, where we have learnt about the various model equations, how conservation laws, it is also very important for you to understand that how to read such kind of problem statements mathematically. So, in this lecture, I shall be giving you some brief introduction to the various ways of the representation of these model equations which you encounter in the transport phenomena. So, what we shall look into? We shall look into the scalar, vector, tensor concepts, some gradient, divergence, curl and Laplacian. These are very common. Understand this. These are dealt with in great detail in the mathematics courses. So, I will not be going into detail of these. I will just touch upon only the minimum knowledge you would require in context of the transport phenomena analysis. So, here we go back to our basic concepts of scalar vector. So, some things you might be knowing, some things may be new to you. Scalar, perhaps all of you have studied that scalar is any quantity or physical quantity that is given by some magnitude. Okay? And many examples are like volume, density, speed, energy, mass, time, etc. So, these are given by some kind of magnitude, like for example, volume we say that say 2 cubic meter, okay. Density of water we say 1000 kg per cubic meter, okay. Some speed of light is 3 into 10 to the power 8 meter per second, okay. So, energy can come in different ways. Sometimes, many a times we talk of the latent heat of vaporization, condensation, okay. Sometimes in terms of specific heat, okay. So, mass you know that we put in terms of say kgs or moles, okay. And time you know it can be also second, minute, hour, days, years, weeks, anything. So, all these things are having just some magnitude. Then we have some scalar function. Now, scalar function what means is this, those functions which have some scalar value. For example, we talk of density. Now, we know that density in itself is a function of temperature, pressure of the particular system. So, we can represent density in terms of these variables like temperature, pressure. So, it becomes a function now, okay. And whenever we are plugging in the value of the temperature and pressure of the system, we get some value of the density and we call this a density function, okay. So, that is how the scalar is different from a scalar function. Okay, whenever it is, we are putting the scalar in terms of some other variables. Then we have scalar field, and this scalar field is defined by the scalar function. For example, if we are considering certain area, certain domain in the space, it may so happen that from at different spatial locations, the temperature, pressure may be different. Okay, so in that case, we have to find the density at different locations with respect to the pressure, temperature. So, we will have some distribution of the density in that given region. So, we say that this is a density field. That means the distribution of the density in the particular region. So, because density is scalar, so it is a scalar field. Okay. Similarly, we can have some variation of the pressure over the atmosphere. So we call it a pressure field. Next we come to the corresponding things in vector. In the vector, as you know, that vectors are those physical quantities which have both magnitude and direction. For example, velocity. Velocity is having a magnitude and also direction, because whenever, even if the speed and velocity, speed is scalar, speed has only magnitude, but velocity has both magnitude and direction. That speed of a vehicle may remain same, but if the vehicle is turning and going on the road, then it is constantly changing its velocity, even though its speed may be constant. Okay? So velocity in that way becomes a vector. Then area. Area, you see that area, it seems many times to us that it may be a scalar, but this is not so. Area is generally a vector, because suppose with respect to some system, what is the orientation of the particular surface. So for example, if I take this particular line, okay, in this particular line, and suppose you are standing here and you have a mirror over here. Okay. Now you see that depending on how this mirror is situated, whether it is slanted or whether it is slanted like this, you will find you will having different kind of images. So what you find that this particular, even though the area of the mirror is the same, but depending on your location, you will find different images. So this you cannot extend for any kind of say flow or some kind of rays. So you will find that if there is a glass here, suppose you have a glass here full of some water, okay, some water is there in the glass. Now depending on the tilt you are giving, the amount of water flow will keep changing. Okay, or some fluid is entering such kind of a system. Okay, suppose you have some fluid entering some system, and like this is the pipeline it's entering. Okay, so there is some kind of means angle. So you can easily see that if this is pipeline like this, or this pipeline is like this, straight. Okay, so that way you will find that different amounts of the mass will be flowing into the pipeline. Okay, so this area is generally, its direction is taken to be the outward normal. That means you take any area, the outward normal to it is its direction. Okay, so that means it has the area, this particular thing, and the directional normal. That is how it becomes a vector. And this is very important in your analysis, as you will see in your transport phenomena. Now vector function is a function whose value is a vector. For example, you have velocity, and you say that velocity is changing over the space in a given domain, in a given region. Then you can see that you have to calculate the velocity at different places. Okay, so this is the velocity distribution. Okay, so that way you are getting the velocity function, as if I have shown you, in terms of x, y, z, in the Cartesian coordinate, in terms of r, theta, z, in cylindrical coordinate, in terms of r, theta, phi, in spherical coordinate. Okay, whatever it may be, it is showing you the spatial distribution of the velocity. And in the Cartesian coordinate, for example, we are showing that this velocity being a vector, it will have three components. So when I say velocity at x, y, z, what it mean? Each of the components is changing with the position. That means where I say V1, V2, V3 are the three components of the velocity. So we have V1 changing with x, y, z, V2 changing with x, y, z, and V3 changing with x, y, z. Okay, and vector field is defined by a vector function. When we have distribution of velocities, we have a velocity field. Okay. Next, we go to see that how we represent a vector in a Cartesian coordinate. You can see this is the black line is showing the vector. Okay, and this is the vector A, and you see that here we have x, y, and z coordinates. So we are putting some unit vector, that means has a magnitude of unity 1, okay, along each of the coordinates. So here it is I in the x direction, j in the y direction, and k in the z direction. This is the convention we follow. Okay. Now you see that in the to reach this particular point given by this vector A, we can resolve it. That means we can make it divide into three components. So first we can travel in x direction to a distance of ax, okay, and then we travel the distance of ay in the y direction, and we travel the distance of az in the z direction to reach this particular point. Okay, so we write that ax into I, that is the vector in the x direction, then ay into j in the y direction, and az into k in the z direction. So this particular vector A is given by these three components in the Cartesian coordinate. Similar things you can also do for the cylindrical coordinate and for the r theta phi coordinate, that is a spherical coordinate. Next, I show some examples to you of the fields. So this is the scalar field for the temperature field over the earth. So this is earth, and you can see that how the temperature differs in the along the various space, that means along various continents and the ocean. Okay, so you can see that there are, and these different colors are showing different magnitudes of the temperature, and this kind of coloring we will see many a times in the books, in the literature, to tell you the distribution of the temperature. In this particular thing, we are showing a velocity field at nozzle. Some exhaust gas is coming out. For example, when a satellite is launched, the exhaust gas come out from the tail. You can see those when you see a picture on TV. You see that some gas is coming out, and that generates thrust, which propels the particular satellite in the space. Okay, and if you can measure this particular velocities or model them, you find this kind of velocity distribution is there, and you can read some of these velocity values. It is given in meter per second, and you can see that they are not the magnitude but also their directions, and they are spreading. Okay, so you see that these values are different and their directions are also different. Okay, so this is a typical example of the velocity field. Next, we come to some very basic operations involving the vectors and some properties. First is the commutative property. It means we can commute. Commute means we can exchange the things. Like if we have two vectors, v vector and w vector, that means if v plus w is equal to w plus v. And when we say this addition, what we are basically adding is the component wise. That means if v is taken to be, if v is taken as some v1i, then v2j plus v3k, and w is taken to be w1i, then w2j plus w3k. The addition means we shall be adding these two, adding these two, and adding these two, okay, in the three directions separately, and that is how we shall get the resultant vector. Okay. Now the addition is commutative. Commutative means the order of the addition does not matter. Then associative. Now you see here that v plus w, the three vectors we have, v, u, v, w. So if we first add v and w, and then resultant vector is added to this u, then we shall be getting the same thing if we take any other combination. That means if I have this v is outside, first we add this w and u, and then we add this v. And you can see that whenever we are adding these two vectors, the resultant vector will have in general both the magnitude as well as the direction different. Okay, you can check it this way, like suppose I am adding these two vectors. So suppose this is the v vector and then I have the w vector. Okay, the resultant addition is like this. Okay, so this is the v plus w. Okay, now you can see whatever v vector has some direction with respect to some coordinate, w has some other direction, and v plus w has some other direction. So it does not matter whether you are doing from this plus this or this plus this, you will have the same magnitude and the same direction. Okay. Similarly, you can extend it for this kind of additions. Now, when we talk of the vector subtraction, what it basically means? Subtract means say v minus w. Now, negative of a vector means what? That it has the same magnitude, but the direction is just opposite, that is 180 degree turn. Okay, so if I say that I have a vector like this, okay, this is, if this is plus v, then just opposite in the direction we have minus v vector. Okay, just we change the direction without changing the magnitude. So that is how we say that negative sign. So once you know the negative v minus w means you have to draw v in the same direction as before, like I draw it like this, and w you were earlier using this, now we'll put in this direction, this is w. Okay, so this is how we are making this subtraction of the two vectors. Next we come to multiplication of a vector by a scalar. So we have a scalar s, and when we multiply this with the vector, we find this is also commutative. Okay, so whether you have s first and then v, or v first and then s, it does not matter. Ultimately the result will be the same. Associative is that suppose you have two scalars and one vector. So first s and v. So first you multiply s with v, and resultant vector you multiply by r. That will be having same vector as if you multiply first this r and s and then multiply by v. And you can extend it the other way also. You can put r into v and then multiply by s. So all of them will give you the same answer. So that is how we say it is a associative. And then distributive. Distributive is that first we have these three scalars q, r, s, okay, and into the v. So this is the addition of three scalars, and that resultant we are multiplying by v. This can be same as that if you take first you multiply q with v, then r with v, s with v, and then add them up. The result will be the same. So this is the distribution. We are distributing this particular thing, distributive property. Then we have scalar product or dot product. Okay, in that what we have, that in this case we have for two vectors. So if we have two vectors v and w, then v dot w is equal to v w into cos phi v w. It means this cos phi v w is the angle between v and w. That we can put in pictorially, that is if we have this v here and if we have the w here, so we have this is the phi vw. Okay, this is the angle it's representing. Okay, so we are finding that this is the way we are defining the scalar product dot product, because here see the resultant will be a scalar. Okay. Next we have the to see that whether this product of two vectors, dot product two vectors is commutative or not. Here we see yes, it is commutative. V dot w is equal to w dot v. Next we go to associative, how we are associating the various vectors. So here we have now three vectors u, v, w. Here you can see that taking dot product first u dot v, then this is scalar now. This scalar is now multiplied by this w vector. This will not be the same if you first multiply dot product of v and w, that is a scalar again, and that scalar you take to be u. So you find that the dot product of two vectors are not going into a commutative way. And then distributive, we see the distribution is obeyed, that is u dot v plus w is equal to u dot v plus u dot w. Okay. And then we have the cross products of the vector. In this case we find that v cross w is defined like vw into sin vw into a vector nvw. Now what is this nvw? Nvw is a unit vector perpendicular to both v and w and pointing in the direction that a right hand screw will move if turned from v to w through the angle this. Now you can see here that in this case we have two vectors uv, instead of vw we have uv. So if we are making u cross v, then from u to v, if you put a screw, okay, you are as if you are putting a screw, then you see the screw will move inside. So this will be the direction of the resultant vector u cross v, okay, where magnitude will be u into v into sine this angle, sine of this particular thing. Okay. So this is how we see the direction and the magnitude of the cross product. Then is it commutative, v cross w and w cross v? No, they are not commutative. Okay. So we should not the order of the multiplication is important. Associative, again we find no, it is not associative. That means u cross v, then first multiplied, then resultant is multiplied by w, is not same as first you multiply v and w, and then first you take the u and cross vw. So these are not associative. Distributive, yes, we can find that u plus v and then u multiplied by w is same as u cross w plus v cross w. Here you should be aware that this w should not, if you put w on the here, then it will not be the same, because w cross u, w cross v, and you find that w cross u is not equal to u cross w. Okay. So this one, and if you keep it at the front, they will not be the same. Now here we put some notations to you which are very much used in the vector algebra, that is Kronecker delta. It is delta with ij subscript, okay, and this is defined as that if this I and j are the same, then we have 1, and if I is not equal to j, we have 0. And you can say here that this is given by some delta, and this Kronecker delta is like as if it is a matrix of d I del ij, del ji and del jj. Del I same, so it is 1, del ij different 0, ji different 0, and del jj same, so it is 1. Okay, in a concise way. And then we have some permutation symbol or alternating tensor symbol. Here you see that we are using some epsilon with I, j, k subscripts, okay, and this is equal to 1 in these cases. Suppose we have 1, 2 and 3. So if we take this direction 1 to 2, 2 to 3, 3 to 1, okay, that means 1 2 3, 1 2 3 or 2 3 1 or 3 1 2. So whenever this is the order of this epsilon, we get plus 1. If the order is the other way around, that means 1 3, 3 2 and 2 1, then it will be minus 1, that is 3 2 1, 2 1 3 and 1 3 2. Okay, for these three cases we find epsilon will be minus 1. And in case these two of these are same, that means if 1 1 k or 2 2 I, some kind of like this, in that case we will find this will be 0. Okay. Sometimes it is also called Levi-Civita symbol. Okay. And now we shall see that how all these representations help us. That now we have, suppose we have these dyadic, we call dyadic vectors. These are nothing but I, j, k in case of Cartesian coordinate. Okay, in theta coordinate also they can be applied. This is more generalized. It does not depend on the coordinate system. So here you have the del 1, del 2, del t, and the vectors. Okay, they are unit vectors. So you see that if you take the dot product of this, delta 1 dot delta 1, delta 2 dot delta 2, delta 3, they are all coming to be 1. Why? Because the delta 1 into delta 1 means their magnitude is 1, 1 into 1, and cos 0 degree between the two vectors. They have the same, they are what we call collinear, the angle between them is 0, so cos 0 is 1. So we are finding their value is coming to be 1. And if we have del 2 dot del 1 dot del 2, del 2 del 3 or del 3 del 1, they are all having the 90 degree to each other, perpendicular to each other. Perpendicular means cos 90 is 1. Okay, so we find that due to cos 91, so this dot product is coming to 0. Okay. Now here I have shown you this delta 1, delta 2 and delta 3 in the Cartesian coordinate. Now here we show the cross 1, delta 1 cross delta 1, delta 2 cross delta 2 and delta 3 cross delta 3. They are coming to be 0. Why? Because sine 0 degree is 0. Okay. So we are finding a cross product of the same thing will be 0, and then we go for the delta 1 and delta 2, it is giving delta 3. Delta 2, delta 3 is giving delta 1. Delta 3, delta 1 is giving delta 2. This same thing as we have just done for the rise to. Here we see that here we take the right hand thumb rule, that here we have that if we put this kind of thing, if we extend our finger like this, okay, like this we extend our finger. So if this is z direction, this is x direction and this is y direction. Okay, so if we go for x to y, then we will get z. If you go y to z, it will give us x. If you go z to x, we will get this y. Okay, So if we alter these things, that means if you go from x to z, we shall be getting minus y. If you go from z to y, we shall get minus x on this side, and if you go from y to x, we shall get minus z on the downward side. Okay, that is how we are applying this right hand thumb rule to find out this dot product. So that is what you say, that 1 2 gives plus 3, then delta 3 gives plus delta 1, delta 3 delta 1 cross, this gives delta 2. And if you change the order, you simply get the negative values. So you can see that the order of placing these unit vectors is important. Okay. And now you can see that delta 1 dot delta j is called delta ij, and delta 1 cross this delta j is given by this permutation vector. Okay. And here we are now expanding a vector in terms of this dyadic vector delta. So here you can see that now we are writing in terms of dyadic vectors, and how is it helping us? It is helping us to make it very concise. Okay. So we are just simply putting summation I 1 to 3 delta I into Vi. Okay. And the magnitude is like, we know that we are just taking the square of each of the components and taking the under root of that. First add the squares of each component and take the under root, we get the magnitude, and this we are putting in terms of these symbols as under square root of the Vi squared, the product summation of the product of the each of the components. Okay. Now we come to the operations. Here we have addition and subtraction. So it is V plus minus W, as I told you that we first put in terms of these dyadic vectors. So you can see that dyadic, this delta I Vi plus minus delta I Vi is equal to delta I Vi plus minus Wi. Similarly, multiplication we are putting in terms of dyadic thing, it is coming like this. Then dot product of this is coming like Vi dot Wi, and cross product is coming like this epsilon ijk delta I Vi Vj and Wk. So you can see that putting this permutation and operator and this Kronecker delta, we are able to become very concise way of putting these additions and summation products. Next is Nabla operator. Nabla operator is generally used to represent the partial derivatives which we encountered many times in the transport phenomena equations. Okay. Now you see that Nabla is given is the space direction. So we see that delta 1 dyadic product, this dou by dou x1, then delta 2, then this dou by dou x2, and delta 3 dou by dou x3, and again we are putting the concise manner like this. Okay. So that means if you are talking of say Nabla T in the Cartesian coordinate, it will look like dou by dou x say t into I, then dou by dou t dou y into j plus dou t by dou z in k. Okay. So this is how we are representing this Nabla operator. So from the Cartesian coordinate. Now understand this, with change of the coordinate system, the Nabla will take different forms. Okay. This you must remember. Now here we have the gradient of a scalar field. Okay. What we understand, gradient is a multi-variable generalization of a derivative. Now while the derivative can be defined on functions of a single variable, for functions of several variables we use the gradient. Like as I just told you, the gradient of scalar field like temperature. So here we are writing gradient of scalar field like this Nabla operator into the scalar S, and this is the way we are expanding it. Okay. This S may be temperature, it may be mass, it can be anything, any scalar. Then gradient increases the order of tensor by 1. That means initially it was a 0 order tensor, this S was 0 tensor, now we are getting a from a vector we have converted to for a scalar we have converted to vector. Okay. So we have increased the order. So here you can see that how it looks like, that fxy is something like this, and then if you take this particular this Nabla, it will take the order by 1 more. Then we have properties of this gradient. It's not commutative, that means nabla S is not equal to S nabla, and then not associative, that means nabla R into S is not same as nabla RS. Then distributive, it is distributive, nabla R plus S equal to nabla R plus nabla S. Okay. And then divergence. Now divergence is of a vector field. Okay. Now vector, when we say divergence, it means that it's a vector operator. It produces a scalar field giving the quantity of a vector. That means in the gradient was converting a scalar to a vector, whereas divergence is converting a vector to a scalar. Okay. And it represents the volume density of the outward flux of a vector from an infinite small volume around a given point. Okay. So any vector is, there is a flux of a vector through a control volume, something is going out, something is coming in. So the net of this, the out minus in, that is the thing is given by the gradient. For example, divergence of the velocity, if you take this you have seen in your in case of your mass balance, you get the divergence of velocity, and you can see that here we are representing these divergences. So if we find that this nabla dot V is more than 0, that means we are getting more output than input, that means there is a depletion. If nabla dot V is equal to 0, that means output is equal to input. Okay. And here you see that if nabla dot V is less than 0, that means input is more than output. In that case, there is an accumulation within the particular control volume. So this is how we are interpreting this divergence of the velocity. Divergence decreases the order of tensor by 1. That means from a vector we are getting to a scalar. Now properties of divergence are this, that this nabla dot V is not equal to V dot nabla, and it is not associative, that means nabla dot SV is not equal to nabla S dot V. Is not distributive, it is distributive like nabla dot V plus W is equal to nabla dot V plus nabla dot W. And lastly, we have the curl of a vector. Curl is generally gives the tendency of some vector field to swirl. For example, if we have talk of the velocity, then if we call curl of velocity, that decides that whether we have a swirl in the flow or not, in the flow domain or not. So we call it rotational flow or irrotational flow. Okay, depending on whether we have the curl of the velocity to be 0 or not 0. Okay. Now curl is defined like this nabla cross V, and this is the way we are putting in a matrix form. Okay. Now you can see if we expand it, it will come like this. So in the curl we are retaining the order, tensor is third order, so it is order of tensor. Okay. And here we have shown the interpretation of curl, that if there is a rotation, okay, then this is the except rotation is rotating. So there is a rotational thing, this is given by the curl of the velocity. And then we have the Laplacian. Laplacian is a particular operator. It generally operates like this, that nabla dot nabla, okay, and given by the divergence of the gradient. That means here we are combining both the divergence and the gradient. Now when we put a gradient of a scalar, it is making it a vector. And then we are, once we have a vector, that means we are basically taking a dot product of the nabla vector with the gradient vector. So here we find that nabla dot nabla S is equal to nabla square S, and here we are getting this particular expanded form for the Laplacian. So this particular thing represents Laplacian. So this is for the scalar field, for nabla square. And where for vector field, again we find that it will have a vector thing. Now this particular thing nabla V, this is neither scalar nor vector, this is tensor. Okay. So this is a tensorial dot product we have to take with a particular vector. Okay. So this is the particular expression for this nabla dot nabla V. And here I have just summarized all this, that if we have this is a Gibbs notation, this expand notation, we call Gibbs notation like this. So if you have expand notation, that V dot W, it is like summation of Vi Wi into summation of this, then in the tensor form we drop this particular summation. So here what we are doing, that omit all summation signs, omit all unit vectors, and replace dou by dou x by dou I only. So dou I means dou by dou xi. So this is how we are making this particular table. So this way you find that in many books, in the many literature, they are putting this kind of notation. and so that they can economize on the space requirement. You can see this particular thing requires a lot of space, but same thing you are making a very concise form for representation. Okay. So, these are the things which you will find. These are the books you can consult for knowing more about these, and I have put this particular lecture to you so that you can read the various transport phenomena based literature which will be having such kind of operators. Thank you.